Okay, so this will be our third example of a test of hypothesis. And here we are going to test a proportion. So let's read the problem. We say that a friend of yours claims to be clairvoyant. To test this claim, you roll assume it is a regular six-faced die, 100 times, and you ask your friend each time to predict the figure on the upper face. Your friend was able to predict the figure 25 times out of 100. So in part A, what are we asking? Again, your friend claims to be clairvoyant, so in A we're asking to test at the 1% level of significance the claim that your friend is indeed clairvoyant. Well, we have to formulate our two hypotheses. As always, we will be under the assumption of H0, and we will formulate an alternate hypothesis. Well, H0 is always the hypothesis of status quo, of no change. Well, we're talking about someone being clairvoyant. Well, the status quo is people are normally not clairvoyant. So this would be the statement of H0. So if you think of it, if your friend is not clairvoyant, then she's just guessing. And each time as you roll the die, there are 6 possibilities. If she is guessing, it means that she will be right 1 out of 6 times. So if we think of P as being the proportion, the probability of your friend being right, under H0, someone being not clairvoyant will be right in the proportion of 1 out of 6. Now, of course, if someone is clairvoyant, in H1, this is the opposite of H0. H0 is, again, the person is not clairvoyant, so he or she is just guessing the figure on each time. Therefore, they'll be right 1 time out of 6. If someone is clairvoyant, this means that they would be right more often. Therefore, their proportion of being right, the probability of them being right, will be greater than 1 out of 6 times. So we have our null hypothesis. The status quo is someone is not clairvoyant, so they'll be right by guessing 1 out of 6 times. If they are clairvoyant, our alternate hypothesis, then they'll be right more often, so P will be bigger than 1 over 6. Okay, so what do we know? Well, we are testing at the 1% level of significance, so we are rejecting the more extreme 1% of values. Because we have a right tail test, we will reject the larger 1% of values. Now, what did we obtain from our sample? We observed 100 observations, right? We roll this die 100 times, and we have found, and I'll use R here for the number of successes of your friend, and your friend was right 25 times out of 100 times. So if you ask now, what is the proportion of times for which your friend was right from your sample of 100 rolls, we'll call this P hat, and she was right R times out of N, 25 out of 100. You can write this as 1/4, or if you prefer in decimals, as 0.25. Therefore, the complement probability or proportion Q hat is 1 minus P hat. 1 minus 1/4 is 3/4, or in decimals, 0.75. So on the surface, it looks like your friend is doing better, right? If she's guessing, she would be right 1 out of 6 times. And for these 100 trials, she was right 1 out of 4 times. So it's a little bigger than 1 out of 6. If you compute 1 divided by 6, it's approximately 0.17. So it seems that she's doing a little better than she would if she was not clairvoyant. Okay. Well, our next step is to look at our test statistic. Of course, under the assumption of H0. here we are testing for a proportion. Now I want to make a comment, and I'll write this up here. If you remember, for a confidence interval for a proportion, we had the following statistic. It was p hat minus, so the sample proportion, minus the true proportion divided by the root of p hat q hat over n. And this is approximately following the z distribution. And here we're okay because we have more than 30 observations. We have 100. The only difference here, when you built a confidence interval for p, the true proportion of a population, we used the estimate p hat for p, q hat for q, because we didn't know the true value of p and the true value of q. But now we are under the assumption of h naught. So we are under the assumption that the value of p is known and is 1 over 6. So we are going to replace simply p hat by q hat by the exact values under h naught. So we'll have as a statistic, again under h naught, p hat minus p over the root of pq over n. And this will also be approximately normal, as we have said, because we have more than 30 observations. So always keep this in mind, that the statistic for a test of hypothesis of a proportion is slightly different than the statistic for a confidence interval for the true proportion. So here's our statistic. The sample proportion minus the true proportion over the square root of the true proportion under h naught times its complement q over n. And as we have said, because we have more than 30 observations, this will follow approximately the standard normal distribution. Well, we have our test statistic. Let's compute our observed test statistic. So because we are observing a z-score, we'll write lowercase z subscript OBS for an observed value of a z-score. What is our p hat? It's a quarter, or 0.25. So you can just write 1/4 minus p, which is 1 over 6. And we divide by the square root of pq over n. Well, p is 1 out of 6 times q. Well, q is the complement of p, so it's 1 minus p. 1 minus 1 over 6 is 5 over 6. And we divide pq by n, and here our sample was 100. Let's compute this. And if you do, you should find an approximate z value of 2.24. So we have our observed z-score. Now we have to construct our rejection region. Since we have the standard normal random variable, we will draw the picture of the standard normal distribution. This is our z-axis, the distribution. It is symmetric about 0. And now we ask, as always, which portion of the distribution are we going to reject? Well, if you look at H1, the claim was that p was bigger than 1 out of 6. So we have a right-tailed test, so we reject the larger 1% of values. So we have to find now the z-score that corresponds to an area to the right of 1%. If you prefer, since our table of the normal distribution gives you the area to the left of a point, if to the right we have 1%, to the left we have obviously 99%. So let's find the z-score from our table of the normal distribution. So the area below our z-score was 99%, so 0.99. So let's hunt in our table of probabilities the answer, the probability closer that we can find to 0.99. And if you notice, it's right here, 0.9901. And so the corresponding z-score is 2.3. Let's move up. 2.33. So you see, if the z-score is 2.33, the area to the left is 0.99, and this is what we have. Therefore, the area to the right is 0.01, and so our z value is 2.33. So we're good to go. So we have a z-score here for 2.33. So we have our rejection region. R will be, again, because we had a right tail test, we reject the right tail of our distribution. So from 2.33 to positive infinity. And as always, we ask, will we observe a statistic that is inside or outside of the rejection region? Well, our observed value for z was roughly 2.24, which is actually outside of the rejection region. So, because our observed z-score is outside the rejection region, we do not reject h0, so we accept it. What does that mean? Well, if we accept h0, this means that we accept your friend was getting the right answer 1 out of 6 times, therefore she was just guessing. So, our conclusion is with the evidence is not strong enough that she is clairvoyant, so we conclude with the conclusion that she is actually not clairvoyant. And that's part A. Let's look now at part B. We're asking in B, what if we had used, instead of a 1% level of significance, a 2% level of significance? Would your conclusion be different? Well, let's see. Right, in part A, we chose to reject only the larger 1% of values, and our observed z value was not part of the larger 1% of values, so we ended up not rejecting h0. Now we are going to reject a little more. Right, our threshold has changed. We said in A, a value is too extreme, therefore evidence against h0 if it's in the upper 1% of values. Now in B, we're saying a value is too extreme, therefore evidenced against h0 if it is in the top 2% of values. And let's see if that will affect our conclusion. And everything else stays the same, right? This does not change, still the same statistic, the same observed value. The only difference, by changing alpha, we will get a different rejection region. So now we are looking at part B. Again, we have the standard normal distribution. We still have a right tail test, so we reject the right tail of our distribution, but now we have a significance level, alpha of 2%. And we must find the corresponding z-score. If the area to the right of our z-score is 2%, to the left will be 0.98. So let's now find the corresponding z-score from our table of the standard normal distribution. So we're looking for a probability to the left being the closest we can find to 0.98. And if we look in our table, 0.9798 is the closest to 0.98. And so we find a corresponding z-score of 2.05. So you see, if the z-score is 2.05, the area to the left is 0.98. So to the right is 0.02. So our z value is 2.05. So we now have our rejection region with a 2% level of significance. The interval from 2.05 to positive infinity. As always, we ask, is our observed statistic, our observed value of the statistic in the rejection region? Well, our observed value of z was roughly 2.24, which now is an element of the rejection region. And so once again, we ask, what does that mean? Well, this interval contains the larger 2% of values. So if you take a random sample under the assumption of H0 that your friend is not clairvoyant, the probability of observing a z value in the interval from 2.05 to infinity is 2% or less. So these are really unlikely values. And what we have observed, again under the assumption that your friend is not clairvoyant, is a value inside this interval. So the odds of us observing a value of z of 2.24 are actually less than 2%. And you say, well, that's rather an extreme observation. It's rather an unlikely observation. And so we start doubting the validity of H0, the claim that your friend is not clairvoyant. So we have evidence here against H0, because if H0 were true, we have observed something that is less than 2% likely, that is too unlikely, and so we choose to reject H0. And if we reject H0, then we end up accepting H1. And if we accept H1, that means that the proportion of times your friend is right is bigger than 1 out of 6, which would imply that we may believe your friend is actually clairvoyant. So you see, once again, the conclusion can be affected by the significance level. And this concludes our problem. And you see whether, and this is our last example of a test of a hypothesis for one sample, but you see whether you test for a deviation, a mean, or a proportion, it really is the same, except you have a different statistic and a different distribution, but it's always the same. In the end, if your observed value of the statistic is inside of R, we reject H0. If it is not inside of R, we accept H0. And that's it.